Thanks again, everyone, for coming, and Tom for presenting the second talk in this excellent series on Simplicial Hopfield networks.
Yeah, thank you. Thank you, Dan. Thanks, everyone, for coming. And I'm going to walk over. Oh, I'm not going to walk over there. Just a moment. I've got to figure out my keyboard here. It's working just a moment ago.
Maybe the window lost focus, potentially.
Yeah. Actually, I'm just gonna.
Zhongtian, I think your microphone is not muted.
I think it's your auto.
I've been having a little bit of problems actually with my USB ports, so I'm just going to swap out for another keyboard.
Sure, no problem.
Yeah, we can just push you around to move the old guy.
That's right. Yeah, Chad is the expert at pushing the bots around from spot to spot. So.
Okay. Webcam, great. Oh, now, yeah, it should be okay. So, just one thing though, Dan. I walked around and I noticed
there's some slides missing at the end. Yeah, there aren't enough of them, so we'll just walk back around here and I'll put the last 5 up.
Okay, sure. Sorry, probably was too many slides. Okay. Yeah, so this is Simplicial Hopfield networks. It's a paper that was accepted at a conference called International Conference of Learning Representations, and the full paper is available there. And I'm happy to talk about it more with you afterwards. And also, I think I'll put if there's not already, I can put a link or a PDF on the Discord. So before I begin, I just want to explain a little bit about the history that got us to here. So first, I wanted to talk about traditional Hopfield networks. Traditional Hopfield networks were made by a guy called Hopfield in 1982. And I want to preface this entire sort of discussion. I'm going to be saying Hopfield networks, but really there's some debate about whether or not we should call them that. And that's because before 1982, there were other people that came up with very similar ideas. And so I just want to acknowledge that that's the case, and that's mentioned in the introduction of my paper. And in the future, actually, I want to possibly not even say Hopfield networks, but rather associative memory networks. But for this talk and this paper, at least, it's called Hopfield networks. So the traditional Hopfield network, you set up some patterns. These are random patterns typically, but they could be structured in whatever way. For example, take on the form of an image with black or white pixels. And those are over some number of neurons, n, capital N neurons. And then we initialize a state to be S, which is normally some random state. Then we update the state according to this update rule here, where you put it through some threshold, and then you're looking at some neuron I, and you look at all the neighbors J in the network. So the network kind of looks like the picture in the top right, where that's an example where n equals 4. There are 4 neurons labeled IJKL. And the edge or the weight between 2 neurons is denoted WIJ, and this one pointing with the arrow is the IJ connection. And so the rule here to update a particular neuron I is to look at all the neighbors J, and then to basically do this multiplication with the weight, and I'll explain how this weight is calculated in a moment. We have the threshold, we consider all of the inputs basically, and this weight is if you haven't seen it before, you might wonder, how do you come up with that? The answer is you come up with it through the energy function, but in a technical sense, but intuitively this is basically like a Hopfield. Well, it's like a Hebbian kind of learning system where these two things here, we're counting the patterns mu to p. P is the total number of patterns, and we're basically seeing how many patterns do we have in common, neuron I and J. And if we have lots in common, then we so-called phi together, and therefore we're going to wire together. We're going to have a positive connection strength if we have a lot of patterns in common, and a negative connection strength if we don't have many in common on average. And this is the taken over 1 over n, but this part doesn't matter so much. And all of this can be derived from this energy function, and these energy functions basically come from physics, but it doesn't matter too much if you don't understand how that happens or why that happens. But just know that that's the case, and intuitively you can think of the energy as like a landscape. In this picture here is an example of such a landscape, which is just a one-dimensional landscape where the energy is on the y-axis and the different states are on the x-axis. So, for example, this blue state might be our initial state, and then when we perform some update, because of this system, we're actually guaranteed that the energy will be non-increasing and typically will decrease. So now if we're in this particular basin of attraction highlighted in green, we're going to be performing some update. We're going to be decreasing our energy down into the bottom of this basin. And ideally, though not always, the bottom of these basins will be our memory patterns, these ones over here. But they might not be. It's not a guarantee. And I'll explain more about that in a moment.
Can I just check if check if I have a correct understanding here? So I suppose in the context of transformers, we'd see something similar, but we would interpret the data that's in these X's as being a vector sitting at node I, right? Where you have a vector of n dimensions. So Xi I mu, as mu ranges from 1 to n, or 1 to p rather, sorry. And you'd think of that vector as sitting at the node I, and that'd be like a query perhaps, and then there would be a key, which is a vector somewhere else, and this dot product is something like the attention that node I would pay to node J. Is that an appropriate kind of connection to make? Or?
Yeah. And I'm going to expressly state that connection, I think, in the coming slides.
Cool.
Yeah, for anyone that doesn't quite follow that. Okay, I'll move on to the next set of slides. So in the traditional Hopfield network, we can have binary patterns. So you can think of the patterns, for example, as plus and minus 1, and if in a picture you could think of those as like black and white pixels. And in the following examples, each row is a different network. And so, for example, network number 1 here has the pattern only of Homer's face, and then the state that we begin with we set to half of Homer's face, and then we perform some updates, and then the new state is Homer's face. So we've successfully recalled this pattern through the network's activity. In the other examples, you see that we give half of Homer's face at the beginning, but we don't recall Homer's full face, and those are for different reasons. So in case number 2, the reason is that we've overloaded the network with Marge's face. So we've actually biased the network, and because there's some overlap between these two patterns, there's some similarities between the patterns, then unfortunately we get the mistake, and because of the strength of the two patterns overriding the Homer's pattern, then we always get Marge. In the third case, it's just a matter of there being a few too many patterns, I guess. And instead of getting Homer's face, we get Bart's face, or an inversion thereof, and actually that that mathematically is considered the same as Bart's phase in this system, like energetically speaking. And the fourth case is a case where there's just too many memory patterns to be had, and this final thing here is called a metastable state. And this metastable state is something that you find a lot. It doesn't have to be exactly this one, but there's basically like all of these in the energy landscape. There's like some deep valleys, but there's also some shallow valleys. And these shallow valleys are the metastable states. And then these deep valleys are your patterns, hopefully. And sorry, the Z's are not going to look particularly pretty on these slides when I write them. Now, theoretically, we should actually be able to store many more patterns than this. In fact, theoretically, we should be able to store about 0.14 times n being the number of neurons, patterns, and be able to recall them all perfectly. And in this case, we have 4,000 neurons because we have about 4,000 pixels. So we should be able to store 570 images. Why can't we? Well, because this theoretical capacity is only for random patterns. And these patterns are clearly not random. They have spatial correlations between them and statistical correlations as well. So because of that, we don't get anywhere near this theoretical capacity. And some of the work being done now is to see, well, how can we improve this capacity, and also how can we go beyond just binary valued data? So that's going to be what's coming up in the next slides. But are there any questions about this one?
I didn't realize the capacity
in general,
was
just
in practice
interrupt me at any point.
This low. This is a real example, these ones you're showing on the slide here?
So the next thing to say, so this is a traditional Hopfield network. So what was found in 2016 was, what was thought was, well, instead of just doing some kind of starting the energy function with what was essentially, well, you can see a few slides ago, we're going to change it, and we're going to make a sort of higher degree set of connections between the neurons. And essentially what they do is they use this function f to do something special, and in this case, you could just use like a polynomial kind of function. So then, in this case, you have x squared is normally the one that they use, and that's where you take the dot product between the pattern and the pattern and the state, and you perform this squaring operation, and then you get, as your update function, this long thing, which looks a little bit intimidating. We're going to break it down in the next slides, but basically you can think of this first thing and this second thing as essentially just the same, and the only difference is this -1 and this +1. So you can sort of say what we're doing is we're finding the difference between, well, if we set our state I to up or down in the first and second cases respectively, are we getting closer to the energy or further away from the minimum energy that we want? Like, we're minimizing the energy if we go up or down. Sort of checking, like, should we flip this up or down? It's kind of just asking that, and then we do that over all the patterns, and then we sort of average it. Well, we take the sign of that, so then we just move in the predominant direction in this case. And if you're wondering how does this connect to the traditional Hopfield network still, in terms of the equations that you saw before, probably it's best seen in the next slides, which I'll move to now. So, whoops. So what is this f function doing? Well, if you just expand it out, then you'll see that in the case of x squared, and then you do some cancelling, then you retrieve exactly what you got originally, but you've just got this extra thing here at the beginning, which is just a constant, so you don't have to worry about it in terms of the way the energy landscape actually behaves. And just a point on notation, here sigma is equal to S, or the state, and capital M is the number of patterns. Apologies, this is kind of a collection of slightly different slides. So you can see that basically by controlling this function f, we control essentially the way in which the neurons connect together. In a sense, these connections are still like this, where you have weights between Uij and all pairs of them. And the meaning of this can be further you can further connect this to attention by noticing that, well, if you expand on this further, well, actually, yeah, we can talk. Sorry, before I do that, let me talk a little bit more about what if you choose some other n. So this is on the next slide. If you wanted to analyze this, it's a bit difficult because let's say you pick n is equal to, I don't know, 10 or something. Then you'll get something a little bit like this thing at the bottom, but it's going to be even longer, and it's going to have lots of different summons of this general form here in the middle. And it's a little bit difficult to analyze. So what this paper here in the bottom right do is that they really truncate this and study a form a little bit like this one, this final thing here, and then they show that it's somewhat similar to, they show that the conjectured memory capacity, which is improved dramatically in this system, is found in this case. Sorry, this slide is a little bit probably out.
Sorry, can you hear me, Tom?
Yep.
Yeah, what's the conjectured memory capacity? You mean conjectured for the overall form with the f is realized when you just take this single summand for the update rule? Is that, and it's still a conjecture for the overall thing, or what statement are you making?
The conjecture that Krotov and Hopfield make in their 2016 paper is, well, it's not really formally stated as a conjecture, but they sort of just they just state that the capacity is much higher, and they don't do much formal analysis. And I think they say something like, what is it? Should be something like, no, I've forgotten the precise statement. I don't want to misstate it, but the memory capacity they tested numerically, and it is improved dramatically. But the way that they did this or tried to show this was kind of hand wavy, in my opinion. And it wasn't until this paper here, the Demer Sigil paper, that they tried to prove this a bit more rigorously. But they, because of these summons being kind of complicated in the general case to prove, they just focused on a case of the final term here, which when they look at the memory capacity is basically improved based on basically the number of parameters that you have. Since when you do this, it's kind of like, so let's say in the case of 3, Whereas previously you had some sort of like matrix of i's and j's. If you have the case of 3, then you kind of have this whole volume of parameters. So you're increasing the number of parameters between all the different neurons, and you're also starting to introduce these connections. So here already they actually have an idea of sort of setwise connections, but they are everywhere, always, and all at once, and also that they're also complicated, of like these forms here. So that this form here, like you have like a connection which is like this. So it's like got neuroscientifically would call this an OR-TAPS, which is like a self connection between a neuron, which is totally legitimate, but then it's also coupled together, oddly enough, with this pairwise connection between two neurons. And then you've got other things where it's like a double OR-TAPS. So these things are kind of weird, and the fact that there would be all of these, like every single one of these things, is quite unrealistic, honestly. And the fact that you sort of don't have any control over it, you just set f. I mean, mathematically and computationally, it's kind of convenient. You just, set your function f and then away you go. But behind the scenes, at least in the interpretations, this is all happening, and it's a bit odd, basically, from a neuroscientific perspective. And so, without jumping ahead completely, but one of the things that we did was basically to say, all right, well, let's not do that. Let's instead sort of have it in a bit more control, and explicit control over the exact number and types of these connections.
Yeah, it's funny, when we were thinking about simplices and so on, I actually wrote to Hopfield and said, do you know of any models that would involve higher dimensional sort of terms in the update rule? Have you ever thought about that? And he actually sent me this paper, and then I looked at it and I'm like, more or less thought along the lines of what you just said. It's like, I took this cube, but first of all, I don't know why, apart from having higher memory storage, I don't really understand either physically or neuroscientifically why that's kind of sensible. And so I kind of just took that as a no, that it wasn't known to him, at least, if there was some sort of Neuro role for terms that had products of 3 factors in them in some Hopfield-like update rule. And then along you come and supply exactly the answer to the question I asked Hopfield. So,
yeah. Well, yeah, I should say it's interesting. I think you and I have talked about other sort of neuroscience or neuroscience adjacent people, and including like Tim Behrens and stuff. There's a diversity of sort of knowledge and opinion about these things. I would say that there aren't many people who think exactly like I do, that there are these obvious sort of simplices in the brain. But anyway, that's also jumping ahead a little bit. I've got a couple of slides on that. Okay, so it's probably been a little bit whirlwindy up until this point, because I'm sort of, this slide I probably shouldn't have had. It's a bit complicated, but in any case, we're trying to get to a connection between traditional Hopfield networks and then expanding them using this function f, and then how does that give us a connection to transformers, like Dan was mentioning before, and I promise that's in the next slide here. So let me just walk over here. So it's totally okay if you're a little bit lost before this. you can sort of hopefully pick up from here. So without even going through all these equations, you can just read this quote sort of in the top right, which is from the paper in 2021, which sort of made the fairly formal connection between at least the spiritual essence of modern Hopfield networks and the transformer, the attention mechanism of the transformer, and in particular, it's where the case of f equals this exponential, and this implies an exponential interaction between all of the neurons, which is unrealistic. But at least mathematically, this is kind of what happens. And the reason for that is because when you do attention, you're taking a softmax, and this has some relation to the exponential function. And you can read through sort of what it would look like to take the exponential function in the modern Hopfield case. It just looks like this, and then of course we don't do the expansion like we did before because there'd be exponentially many terms. And there's a small difference, I think, in the notation here, but it's not too important. If you're interested in these details, I suggest looking at this paper. Beware though, it's written by physicists.
Is this the Hopfield networks is all you need paper, or is this a different one?
The 2021, this one, this is the Hopfield networks are all you need paper.
Yeah.
And the de Mersagill, I'm sorry for mispronunciation, paper in 2017.
That's got this. That's got these equations in it.
Yeah.
I see. Mm-hmm.
Yeah, and they have two proofs for different memory capacities, which are sort of, I think, ultimately exponential in the number of neurons in terms of the memory capacity. Most of the time, when we're talking about memory capacity, we talk about it in terms of the number of neurons. In my paper, I actually have some statements and corollaries which are to do with the number of parameters, because I think actually that's what matters. It's not the number of neurons. The reason why people think that it's the number of neurons is because typically they don't control for, or they don't actually count the number of parameters per neuron, or like in some sort of non-global way, because, well, with everything that's come before and that you've seen in these slides so far, all of the connections are basically the same everywhere, and then the number of parameters is basically tied to the number of neurons. Whereas in my network, although that's true, it's not true quite as reliably, let's say. So the outcome of all this kind of playing around with the update rule and basically the energy function underlying that is that you get improved memory performance. So now, in this example of some different Simpsons characters, we can have, for example, all these different patterns embedded. These are two different networks here, and you can get perfect recall of Homer's face. And actually, the memory capacity is something like this, where n is the number of neurons. So here, in this example, if we had 4,000 neurons, we could have about 10 to the 29 binary patterns if they were random. But of course, these aren't random. Okay, so we've had some success in the sense that we've improved our memory capacity. But underlying that, as I sort of alluded to, there's some neuroscientific iffiness if we want to keep having a neuroscientific implication. So let's move on and start thinking about some of those implications. Oops. So the first implication is still a more theoretical one, and that is, well, neurons don't have just on or off states exactly. And indeed, for a long time, people thought about the states of these Hopfield networks might not be exactly the states of individual neurons, but rather the firing rates, that is the sort of average activity of a small collection of neurons, like what I called last time in the last talk, an assembly of neurons. And so people have thought about, and even Hopfield thought about this, back in the 80s, as well as others. Well, what if we made the variables continuous? And so instead of the patterns being and the states being in sort of this binary system, let's not have that. Let's have them take on real values, typically between 0 and 1. So it's a range, and then you still have the same system as before. What you then do is you arrange these patterns into a matrix like this. So you have P many of these patterns, and then if you know the equations for attention, you'll think, okay, this is basically now attention. This update rule, and this beta parameter is like the sort of the temperature.
I think there's a logarithm missing in your log sum exp.
So, sorry, could you say that again?
I think there's a logarithm missing in your log sum exp. Maybe you want a log here.
Oh, yeah. Oh, yes. Correct. Yeah. Sorry about that. Yeah, that's correct. Yeah. Is there anything else missing?
Not that I can understand. No.
Yeah. Thanks for that. Yeah. So now you, in order to calculate the energy, you have this log sum x that you use, and I won't talk about how this comes about or why, but just know that these are the equations for having a continuous modern Hopfield network case, and it comes from the energy originally. Like you can drive everything from So in all these cases, if you know the energy, in this case you need to know this function as well, you can derive the update rule and other things. Now, what does this give you? Well, on the next slide, you'll see that now we can have continuous patterns. So these are sort of grayscale patterns, and Homospace has got more detail and nuance to it. And this is a case where we had all these 24 patterns here of different people, and this beta parameter is basically how much do we interpolate between the patterns. So if beta is high, then we're going to recall more precisely this pattern, but if it's not, then we're going to sort of smooth out and average across more of these patterns. And that's a sort of imprecise way of talking about the energy landscape, which we're going to talk about in the next slides. But just before we do, are there any more questions about what I've talked about thus far, realizing that probably I've talked a lot?
Not from me. Maybe I could just comment on, there's a kind of difference in emphasis, I suppose, from the Hopfield literature and the neuroscience literature sort of talks about these models in the context of memory recall, whereas I suppose similar looking systems would be just used to fit to a model, I guess would be one way of putting it. How do you think about the relationship between those two? Are they just two different ways of saying the same thing, or they're essentially different?
I think they are essentially the same, in the sense that so there's also been work by Schmidhuber and others who've made the connection between attention and just like regular old vanilla feed-forward neural network optimization. And in that case, and in all these other cases, the more I think about it, the more I think that, yeah, just fundamentally, when we train and optimize a neural network's parameters, what we're really doing is we're asking it to make sort of some interpretation rules, which are interpolating between the memories of the training examples, and then when you see a new quote unquote training example, that is like a test example, tell us, which one it's closest to, or tell us which combinations of things it's closest to. And so in a sense, everything that I see, now I can interpret as a Hopfield network, or as sort of memory recall dynamics that we see classically in the hippocampus, but also in other areas of the brain. That's not to say that such a simplification is a good one to make, but it's just the one that I sort of intuitively go to a lot now.
Mm-hmm. Mm-hmm.
And at least that helps drive my intuitions for all this. So even though, my focus is explicitly about memory recall and not a traditional sort of optimized neural network case, I sort of view those optimized neural network cases as types of memory recall.
Mm-hmm. I've seen some work out of Tim Barron's lab, which is commenting that patterns are a form of memory themselves, right? So you can recall Homer Simpson, but also the social graph that relates his family is a kind of thing, like an image of Homer Simpson, and that these transformer-like models are perhaps in part matching what you give them to recall both the content and also the relationships, if I remember that paper correctly. Is that consistent with how you would think about? I mean, there's not just recollection, there's also sort of computation, right?
Yeah, that's right. I mean, in terms of the dynamics of the recall, then that can happen. Yeah, like it can be more complicated than just auto-association, for example. It can be heteroassociation, or it can be so like auto-association is like, I give you half of Homer's face and you give me the whole image of Homer's face. But there's no reason why this projection needs to be onto the same space, let alone, not just the image, but it can be onto the family tree or it can also just be onto a larger space or a different space in quality and content and all that. So, definitely agree. And there's a nice paper called Universal Hopfield Networks, which talks about this general schema as well, about basically you have some different key components of these associative memory networks. Actually, so I think it might be called a Universal Associative Memory Networks, potentially not Universal Hopfield Networks. But this last step projection is what I'm talking about, which is not necessarily just to itself, not to the same sort of base space, but some other space potentially.
Cool.
Okay, so I'm going to talk about the energy landscape now. Let's see. Yep. So this like interpolation stuff between memory patterns, like what do I mean visually speaking, and also potentially neuroscientifically? Well, on the left here, the 2D energy landscape, you can think of there being these deep valleys. So we're sort of like looking down on the energy landscape, and then the lighter color means like a deeper point in the energy landscape. So that's like a lower energy value, and then the darker shaded regions have a higher energy landscape, a high energy value. And so these dots are are patterns that we put into the network in this small 2D example. So we've just got 2 neurons here actually, and we've set these. So you can think of these values as of 2 neurons, right? And this is just the different XY coordinates of those 2 neurons. And what we've done is we've sampled the energy at all these spots, and we're classifying the dynamics of different places. So the crosses are actually fixed points dynamically, so they're close to the patterns as you would want. You would see that and you also see the energy is kind of smoothing out and sort of making it so that if you start here, you perform some update, you get down to where you want. And if you're here, then probably you'll end up in one of these. And this circle here around one particular pattern is indicating that this whole region is guaranteed to converge to this point. It's some sort of theoretical guarantee, but in practice, even if you start all the way out here in the corner, the update will let you go down the energy landscape, and then on average you're going to follow this and go to the nearest pattern. But what happens if you increase the if you change the location of the memory patterns, or if you change the temperature, then you can have these metastable points, which are shown in M. And if you decrease the temperature too much, actually this is the inverse temperature, then you're going to make it so that even though you have these patterns as distinct points, you will converge sort of to the average of all these patterns, which is not necessarily something you want if you want to recall the individual patterns, but it might be something that you want to do if, for example, you don't necessarily care about the particular member in a family tree, but you just care about the generation or something like that, to use some different language or some different examples of memories instead of just pictures. And the next slide here just shows some more examples. This is with, I think, something like 10 or 20 different patterns. And in this case, the green dots are fixed points. And what you notice is, in general, the energy landscape gets sharper when you increase this beta parameter. So it goes from 1 fixed point up to 2, and then at 4 it's kind of stable. Unfortunately, though, it can't remember, and it can't sort of split up the energy landscape much further than this in this case.
You could say unfortunately, but also you could argue it's a form of generalization, I suppose, right? Where it's maybe showing you a generic cat or whatever, if I remember.
Right.
Yeah, I had a question about when I looked at the I forgot the other author, in addition to Hopfield, with the X to the N paper.
Krotov?
Yeah. So the Krotov-Hopfield paper, when they're using X to the N, yeah, they have examples where it's sort of, they're trying to run it in a generative mode, if I remember correctly, but it sort of just reproduces exactly one of the training images, which is kind of not what you expect a generative model to do. And that's maybe to do with, would I be correct in thinking that's sort of to do with this picture, perhaps, where if the fixed point was literally on one of the black points, somehow just because of their distribution, you'd always recall that one if you feed in a little bit. But in some other cases, you might start the dynamics in a place where you end up in one of these averaged cells where the fixed point is, I guess it always is one of these black dots in most of these pictures for the low temperature.
Yeah.
Yeah.
It is.
So in that case, if I fed in even exactly one of the other training images or whatever you want to call them, I wouldn't get it back. I would sort of get this very heavily weighted guy nearby, right?
Yeah, exactly. And it wouldn't be something that you can even explicitly control. It would sort of just be a property of the distribution of the memory patterns, rather than something that you want to control. And indeed, it would be, instead of some nice, say, generation of interpolation between these memory patterns, it would rather be an exact one that is somewhat arbitrary to you. So I suppose, that's an important acknowledgement, is to say that, although I was saying that it's a negative, it could also be seen as a positive.
Could I ask you also about the shift to the continuous values? Because I know Ben and Zhongtian and I have talked about this a little bit. I didn't quite. I found it very interesting, the comment you made about the justification for that. Could you repeat that perhaps? So I think about these continuous values as averages of more fundamental units that are maybe still discrete, or how?
Right. Yeah. So you may recall, and for anyone who wasn't here last week, I think Dan's put the video on Discord, a link to the video recording of last week's talk, where I talked about so-called assemblies of excitatory neurons. And in the brain, basically, there are these functional units of, let's say, tens of neurons. And those neurons all kind of correspond to some memory item or some salient feature in the environment or cognition. And in the case of Hopfield networks, and also these sort of abstracted pointwise networks, pointwise meaning kind of like we have a whole bunch of vertices in a graph, and each of those vertices represent, typically is said, a neuron. Well, another interpretation that a computational neuroscientist has, especially when you make those variables continuous on the graph, those vertices, for example, in the continuous Hopfield network, are associated to real values. We might, instead of saying each one of those vertices represents an individual neuron, we might say that each one of those vertices represent an assembly of excitatory neurons or some other neurons.
I see.
And then that would sort of let you take an average of their population activity, and then you would think about, okay, well, then it makes sense to associate a real number. If there's only on or off, then it kind of lends itself more to this spiking analogy. So neurons can either be on or off in that sense, they're either spiking or not, but they're more often quiet, actually. So the average firing rate would be kind of far too high in most Hopfield networks for that analogy to hold. So you may still wish to sort of think about some thresholding of activity of the assemblies of neurons at each one of these vertices.
So there's a built-in hypothesis there, which is actually similar to the idea of renormalization in statistical mechanics, which is that the relevant dynamics can be summarized at the level of the assemblies, right? That the update rule kind of says that the average activation in this cluster is a function of the average activation levels in the other clusters and some kind of notion of weight between them. But that's sort of working at a higher level than the individual neurons and the original sort of set of ideas in the Hopfield network. So do you accept that kind of idea, that it's true that the updates between these collections or assemblies or whatever is mostly can be factored through those high-level assemblies rather than in interactions between individual neurons in the assemblies that can't be so described in terms of the assemblies? Is that neuroscientifically valid, do you think?
I think that's probably more valid. However, computationally and physically speaking, that's going to be less efficient because you've got more stuff. Of course, in our computational systems, it sort of doesn't matter. Like, we can just have all these things as be precise, individual, discrete values. But implementation in wetware in brains probably is not going to be. It's not going to be possible to hold these values perfectly in anything but assemblies. So I would say it's more valid.
Has anybody done any experiments to? I mean, if you set up those assemblies like that. I mean, it would be interesting to see an experiment where you can actually show that even if you run the dynamics at the low level, the behavior still is captured well by running the analysis as though they were continuous values and interacting according to the continuous Hopfield network. Is there anything like that?
There is a little bit. Let me make a note, and I'll post something on Discord after this. But yeah, there is some stuff like that. I mean, the part of the reason why there's probably not a lot is that you'll probably see a look of disappointment upon most neuroscientists' face when you talk too much about this, because they would like there to be, and I personally would like there to be, highly efficient algorithms which don't rely on assemblies, because part of the beauty and wonder of these individual neurons is that they are very sophisticated beasts unto themselves. And it would be a shame if we had to have a certain number of them to do anything special, because they seem to do a lot of special things just on their own. So, of course, not everyone would share that view, but I think many people would be a bit sad. But let me post something on that.
Yeah,
so
thanks.
kind of about cell assembly dynamics.
And I don't want to derail you any further. You have many more slides to get through, so I guess we should.
It's fine. It's fine. I apologize as well. I probably overdid it slightly on the slides, but this time. But I kind of thought, given the opportunity to talk about some of these things in depth, why not? All right. So now we're talking a little bit about the interpretations of setwise connections in biology. So I think this is one of, strangely enough, this was just an obvious kind of thing to me, but it seems like it's not obvious to many others. But let me go over some examples of so-called setwise connections in biology. So we talked about, like in the modern Hopfield case, that we're implying a whole bunch of odd connections in the brain and between neurons if we let these kind of terms, these larger high dimensional terms, come through. And people have complained that that might not be realistic, but I say it is realistic, but it just has to be not everywhere at once and everything at once. So here's some examples that we can think of. This one here, A, on the left slide, is called a multisynaptic baton. And that word, that last word is this. Multisynaptic. Well, synaptic is like a synapse. That is a connection between neurons. So you can see there's one synapse here and one synapse here. And then this whole structure, this whole cartoon, is a multisynaptic baton. And what you have is you have three neurons, K, I, J, and K is synapsing onto the terminal of J. Terminal just means like the end point of J. And it so happens that at that terminal, J is also synapsing onto I. So in this case, when K fires this synapse, because of the biophysics of this synapse being so close to this one, we're going to have a strong positive current in this section of J, and that's the condition which lets this synapse become active. And so in a sense, and you'll also actually get some positive flow going that way in J, and then that might have some other effect on J. But in a sense, what you've got is an activation of three of these neurons, at least in these parts of the neurons. And in that sense, you have a connection between all three of them. Now, in order for the traditional, well, I wouldn't say, maybe not use the word traditional, but at least the normal setup for these Hopfield networks to work is that you would have to have a symmetric connection going in the other two orientations of this. So from like J to I to K, and from I to K to J, at least to be balanced in one sense. But you would have to have all possible combinations in some other sense. In panel B, we've got a case of dendritic integration. This word dendritic comes from dendrite. Dendrites, if you've seen a picture of a neuron, you see all these wonderful little things falling off it, and then you see some long thing like this. This thing is the axon. And and these things up here are the dendrites. And the dendrites are sort of like a complicated spaghetti of integration where there are lots of these synapses, lots of these points of contact like this between J and K, where they combine together and integrate their electrical fluxes that are caused by these synapses, and then they can combine together. So if neuron I, which is what we call the postsynaptic cell, the one being affected by the neurons J and K in this case, if I was already active and then J and K were active, but it was a condition in order for their activities to sort of sum together or to be effective on I, let's say that they both need to reach some threshold and have some kind of like AND operation here, then it would be the case that you sort of have to have a set of connections, or it causes a set of connections in some functional sense between J, K, and I. And what's interesting about these examples is that like a slight move of these, like a physical move of these synapse locations, which can happen, dramatically changes the integration as well as the shape of these dendrites. So the precise kind of biophysics here matters a lot and is plastic and changes under learning conditions.
Are you saying that? Yeah, I'm super interested in this example for reasons you understand, I guess. So the formation of this precise configuration happens potentially during learning, and is this and the role of conjunction here was this something you noticed, or do people literally talk about this, or is it just sort of subsumed in a more general discussion?
Yeah, this is subsumed in the general discussion of dendritic integration. And this is like an extremely fascinating topic, which, will delve into all the biophysics of this. And, I've mentioned but a few of the variables which affect the unique configuration of these things. But all of those variables, well, not all of them, but many of them are plastic and highly important to the functioning, of these sort of little specialized AND operations or operations or all sorts of things that can happen and can occur. And I'm only talking about the case of like the quantum or the strength of J and K being symmetric or identical, right? You can imagine there are other cases where they're not. You can imagine that, you have some other thing here or here or, here that interacts linearly or non-linearly. There's so many different things that can happen. And also too, normally we talk about there being sort of like positive and negative charge that, is sort of just like the sum of all the ions and the net sort of charge that's there, and that's normally what matters when we're talking generally. But actually what matters and more precisely in general is the exact makeup of those ions and charges. So when I talk about like positive and negative, I'm really just already making a simplification. And you could have theoretically overlapping or interacting, or independent kind of systems going on with those different ions. And actually, if you're interested in this general topic and some of the complexities that can arise, not just in neurons, but just everywhere, because within these structures is of course within the neurons, but then there's all this extra space out here, right, where you have ions floating around, positive and negative and all different types. And it's been proposed recently, well, we should also think about that space and what computations could happen in those spaces. Obviously they're more continuous and spread out, and there's more complication there. But if you're interested in that, people have proposed recently to do that in the C. elegans model, which is like a very basic worm. And in particular, a guy called Conrad Cording has proposed this.
Ah, cool. Yes, I'm a fan of coding.
Yeah.
This is, I get a little bit of an insight into the overwhelming complexity and how hard it is to even just start to choose what to model in doing all this.
Yeah. Yeah, I mean that there is just so much, and so and these cartoons don't do it justice at all. And I already got a few laughs from colleagues of mine who work on much more detailed models and systems in neuroscience than I do, because these cartoons are so simplistic. And maybe in the interest of time, I'll just mention C, and then I don't know, maybe one more in the other slide. C is just a case of, well, if you have two connections next to each other, two synapses between two independent sets of neurons, or independent pairs of neurons, it can absolutely happen that when you send a signal from one of these, if you send a signal between K and, I suppose this should also be labeled, let's say between K and L, then there's sort of there isn't like a direct connection here between K and L. What's happening is you actually release something called neurotransmitter, which are these little sort of signaling molecules, and then they get attached to the postsynaptic cell, the cell you're trying to affect. But they get sent out sort of everywhere. They mostly are kept within this space called the synaptic cleft, but they can, there's no rule saying they have to stay there. And so they can wander off and affect a neighboring cell. And in that sense, you have connections which are not just, in between pairs of neurons, but also groups of neurons. And D is a case of connections between assemblies of neurons. In the next slide here, I talk about how some of these things...
C seems like much more of a stretch than A or B. Is that reasonable? Is there like a lot of evidence
it's
for
rarer.
C? Yeah.
There is evidence for C. There's direct evidence for C in hippocampus, but it's rarer. I think the most common forms of these setwise connections probably come in dendritic integration and also astrocytes.
Right. What's the name for C, if I wanted to look up more about that?
C is called like extrasynaptic what would you call this? Extrasynaptic neurotransmitter. I'll just put NT diffusion.
Okay.
Yeah, and I do in my paper in Appendix A2, I believe it is. I have a reference for all of these cases, and at least one reference, normally two or more.
Cool.
And so, apologies that I'm kind of going over time.
Yeah, that's fine, but maybe you want to get to your model rather than give us more examples.
Let's skip maybe the modulation ones. Abstract simplicial complexes. Does anyone want me to explain what an abstract simplicial complex is? Happy to, but speak now or I might skip it. Okay, I didn't hear someone asked me to stay on that, so just read that slide. If pause the video now if you're listening to the video and don't know what an abstract simplicial complex is. So the way that we model our case is we have simplices, which represent the setwise connections between neurons in our case, and that's kind of like that f function if you put it to some power, and then choosing, like by choosing different simplices in the simplicial complex, you choose which particular connections you keep or don't keep. I've kind of thought that perhaps a hypergraphic structure is more appropriate, since simplicial structure, in a sense, if you have a high dimensional connection, it would imply through downward closure that all lower dimensional connections also exist, but between the different subsets of that simplex. But that's not necessarily the case. Like, for example, we didn't get time to talk about it, but astrocytes connect neurons which might not be connected pairwise. So that's something to be said. But in that case, just think about it like a weighted hypergraph where the weights on the edges are the sort of connection strengths. In our case, we just choose to weight some of the simplices as 0, and the non-weighted simplices are the ones we're counting as parameters. And then through a generalization, which is very similar to what you've already seen, we just count basically within some simplex how many patterns do these neurons have in common. And if they have many in common, it'll be a positive weight, and if they have few in common, it'll be a negative weight. And through that, you get sort of Gaussian distributions of weights across the different levels of simplices, even though you get definitely different numbers of absolute numbers of these weights, since there are far more, for example, 3 simplices than 1 simplices on some, on the same n number of neurons. We could move on to the next slides unless there's a conceptual
Yep,
point.
Let's do that. So let's run back to the beginning, everybody. Yep. Chad somehow was already here. Okay, let me just put these up quickly. Maybe if anybody has questions about the last couple of slides, they can ask. Yeah, I'm curious in the comment you made about the there are, of course, many more higher simplices than lower simplices, and in principle that can just swamp. You have an intuition that, probably it's the pairwise relations that are the most important, and it should be refined by the triples and further refined by the quadruples. And that's, in your view, supposed to be learned, or is it part of the design of the update rule or something?
Yeah, interesting. So I think that basically the strongest connections neurophysiologically will be those pairwise connections. I'm not sure about that all the time is going to be the case, but I think that that's the case. And because I think that might be the case, I think that's why they sort of exist. Yeah, why there are more of them. But it might depend on what you care about. Like, what I was caring about here and what I was testing in this study was auto-associative recall, like give half a pattern and try to get out the whole pattern. If you cared more about, say, interpolation or averaging of stuff, then you might not actually want so many of those pairwise connections. You might actually be happy with the higher dimensional simplices and more diffuse average activity. So I think it might also matter a little bit about what you're testing, but at least so far, and I haven't thought about this heaps, but I think that the high dimensional stuff exists, that there's so much of it that exists, even through just, say, dendrites. But the connections or the functional consequences of those are less than some of the pairwise connections.
Got it. Did I put these? Yeah. Am I missing a slide, or is this supposed to be the next one?
I think that's correct. Yeah. Okay. So I'll just get out of the way of the orb cam in case I'm in the way. So the following are sort of some of my results, and we just tested low-dimensional simplicial networks. That is, like, not with heaps of high-dimensional simplices. And we also didn't want to test something with more parameters than the traditional Hopfield network, because that's kind of cheating, right? So what we did was we set the total number of parameters as n choose 2, where n is the number of neurons. And then we had the following conditions. labeled K1 through to R2 in this case, and these different labels like R12 25%. R means random, 1 2 means that we have 1 simplices and 2 simplices, and 25% means a 25% loading on the higher of those two. So that means 25% of our loading of our parameters is in the 2 simplices and 75% on the 1 simplices, and so on. And R2 is just a random selection of 2 simplices. So these are the simplices that we choose to weight in our particular network, and then you can see our results in the next part of the table, where we have different loading of memory. So starting at 0.05 n being the number of neurons, up to 0.3 n, and you might remember the traditional capacity for a Hopfield network was 0.14 n approximately.
Sorry, can I just check? I'm looking at table 5 now, or am I still on the first slide?
Sorry, on the first slide, on the left.
Okay, sure, yeah.
Yeah. And so K1 here is the traditional Hopfield network. And the traditional Hopfield network has that capacity about 0.14. So you can see here a value of 1 means perfect recall, and 0.5 means chance. These are binary patterns that we load into the network, and you can see that there's a big a difference between, and these are just some numerical simulations, so they're not perfect. You can see that there's a big difference there where it goes from about 80% down to 66%. Whereas if you look at our high dimensional analogues, which don't have more parameters than the traditional Hopfield network, they actually perform quite nicely. And in fact, even this one here at approximately double the traditional capacity is performing about as well as the traditional Hopfield network is at a much lower memory loading. So these results sort of indicate that the high dimensional weights are important, but it's not just that you have a large number of them; they're actually more meaningful or more impactful on the dynamics. Interestingly, though, R2, which is only high dimensional ones, it's like only 2 simplices, performs pretty badly. So you need some of these. Apparently, you need some of these low dimensional simplices in order to, I say, kind of balance out and affect the dynamics more precisely.
You say pretty badly, but it seems better than K1, is that right?
Yeah, at least initially, right? Yeah.
I see, but it drops off faster, and so you
drops off faster, yeah.
And you're saying, at least compared to R12, 75%, it's clearly...
That's true, yeah. Yeah, these comparisons here, right? But yeah, it's just at this point it goes badly. Goes pear-shaped. Yeah, actually, so there could be some phase transition thing happening here. Hadn't thought about that, actually. I hadn't looked at those.
So these are random patterns, you said, right?
These are random patterns and also random choices of which simplices to weight, except that, with these proportions. Yeah. And I think it's 100 instantiations of each network, tested 100 times each, so that's quite a few. I think numerically this is fairly robust. We also tested the homology of the simplicial homology of the underlying simplicial complexes that we were making. Like if you consider just the weighted simplices, but there wasn't really much relationship between that and the performance of these models, interestingly enough. And then the next tables here show, what is this? Oh, this is just some slightly high dimensional stuff. It's basically the same story, tables 4 and 5 on the right side here. but now the way that I'm notating that, notating the sort of distribution of simplices is with a little bar above the dimension with the highest proportion. But you can see all those proportions kind of spelled out in this key in table 4. And yeah, it turns out if you have even higher dimensional stuff, it performs even better. And then moving on to the last few slides, we did this with continuous patterns as well. And we tested MNIST, CFAR10, and Tiny ImageNet. So those are different sort of images with continuous values. And we just tested the R1 to 75% one. And in this case, it performs better in basically all these cases. And these different colored lines here, there's also a typo, that should be Manhattan with an A. And yeah, all these different colored lines are basically different distance functions. And maybe we don't have time to discuss that in detail, but it's in the paper. Basically, when you consider, and this is inspired by the paper called Universal Associated Memory Networks, they tested different distance functions, basically different sort of geometries in the space, and it showed that Manhattan distances actually perform quite well. These two things here, CED and CMD, are sort of high dimensional analogues of Euclidean distance and a kind of volumetric distance, because when you're dealing with high dimensional stuff, you sort of have some extra choices and ways to measure distances between, let's say, the memory patterns and the states.
So I read, for example, in ImageNet, I'm paying attention to the kind of pinkish red line in both cases and noting that it's very high in the bottom row with simplices and kind of as a similar trajectory, but always, I mean, even at 1000, the R12 model is doing better than K1 at 200, right?
Yes. Yep.
So that's and again, this is at the same number of parameters, right?
Sorry, could you say that one more time?
So both of them have the same number of parameters, is that right?
Yeah, that's correct. Yeah.
Okay, so that's quite a difference.
Yeah.
So it must be true.
lastly,
simplices in the brain.
Sorry, what's that?
How could evolution not be making use of this amazing technology? Must be simplices in the brain.
Yeah, exactly. Yeah, I think it's. Yeah, I think it must be. And as a small sort of backtracking to the stuff about energy landscapes, I'm not going to go through it, but the more triangles you have, like the higher simplices you have, the sharper some of the cliffs and valleys and things are in your energy landscape, it seems. And okay, yeah, so that's the end. The summary is on the last slide there, just basically saying that sparse random connections improve memory capacity, and our results offer a way to improve memory in transformer models, we hope. But there's also neuroscientific implications for things like astrocytes and dendrites and their function.
Yeah, thanks very much, Tom. It's fascinating and clearly a lot more to do. If you had to, I mean, you could guess that, okay, maybe this is better in some sense, but it might be harder to find the model that computes this way than the model that computes with just pairwise attention or pairwise connections in a Hopfield network. Do you have any comment about that? I mean, if there are indeed structures in the brain that do this, I guess maybe it's not such an obstacle, but the more complex thing, even there's some selection pressure and statistical reasons to think that the more complex model might not be preferred ultimately, even if it's better. So,
yeah, well, one nice thing about what we showed is that you don't have to be clever about your choice of this high-dimensional structure. You can just randomly choose things. So that already gives like a nice starting point. And I think, I don't quote me on this, and I'm not sure about this, but I think that given that starting point, probably you can optimize things fairly easily from there towards an okay-ish structure. What's interesting now is to think about, well, how do the different like a lot of work has been done in terms of neuroplasticity in the brain, thinking about essentially just pairwise connections. There's very little, but it's starting to happen now, about what happens between plasticity in some of these high-dimensional connections. Astrocytes being probably the most famous example at the moment. So I think that needs to be teased out a bit, and once it is, we might find that the brain is quite good at coming up with clever high-dimensional structures.
Yeah, fascinating. Is that, I mean, there are many ways in which topology seems to be being brought to bear on neuroscience, but most of them, as far as I understand correctly, are more like our tools for describing the phenomena rather than making an assertion that nature somehow discovered this trick. First of all, is that an accurate understanding? And secondly, do you think this is the kind of, like, one of the primary ways that we might find evidence for more sophisticated topology in the way that nature computes?
Yeah, I think so. I think that's accurate, and I think that's accurate about like what people have tried to do before and what I'm trying to do. And yeah, I think this is just the beginning. That there can be many different ways where we can, at least through an interpretation, think of the computations and capacities and wonderfulness of the brain is somehow in the way that it utilizes high-dimensional structures or things like geometry and topology and all that good stuff.